Hello everyone. My name is Cynthia Henson and this is SFU's Café Scientifique. Thank you for joining us tonight. At this time, we will just give it a minute or so and wait for more people to come into the room. But for now, thank you for joining us. This is brought to you by the Dean of Science office over at Simon Fraser University, and we do this at least 6 times a year. So we appreciate your joining us tonight. I see lots of familiar names coming into the participant list. Thank you so much for always joining us every month. And a warm hello to those coming in for the first time. This is our March session, our 3rd session of the year. And after tonight, we will have one more for the spring term and we'll continue on in the fall term. But for now, we'll have someone from physics, and I'm glad that you're all joining us tonight. All right, I have 5:02 in my time. We might as well get started. So my name is Cynthia Henson, and I work at the Faculty of Science over at Simon Fraser University, and this is an event called SFU's Café Scientifique. This is a discussion series where we invite various faculty members from the Faculty of Science at SFU, and we ask them to present a little bit of their research. And this allows the public to engage in conversations with our faculty members on these research areas. So we're happy that you're able to join us tonight. We hold this, as I mentioned earlier, we hold this at about 6 or 8 sessions a year, I would say. And we're keeping ourselves virtual for now. After tonight's event, just a reminder that we will be sending a feedback link to all those who've attended our webinar for tonight. We look forward to receiving some of your comments and suggestions for this series. Also, because you've registered for this event, you will also be receiving emails on the next events so that you receive the registration links as well. And we hope that you can join us for the next event. We're happy to see lots of cafe regulars. Thank you for always joining us each time we do this. And a special hello to all those joining us for the first time. We do have some registrants coming from out of province. Thank you so much for engaging with us tonight. Let me begin by acknowledging that we are privileged to gather today on the unceded traditional territories of the Squamish, Tsleil-Waututh, Coquitlam, and Musqueam peoples. We thank them for having cared for these lands and waters since time out of mind, and we look forward to working with them in partnership as we continue to build this great city together. If you know whose territory you're currently on, please take a moment to reflect on this. And if you don't know whose land you're on, I encourage you to look it up and make yourself familiar with the Indigenous peoples whose land you occupy. Just a few house rules before I turn it over to our presenter for tonight. We do have a Q&A box on your screen. Please use that to type in your questions or comments. We would love to hear from you and for you to engage with our presenter. We will try our best to read out all the questions and comments after the presentation. The chat page is turned off just to simplify and just for you to have access, please, to the Q&A box. However, there's a live transcript. It's been turned on. If you find that helpful, that might be convenient for you. And also just a reminder, this event is being recorded and we will share the material publicly on our faculty website and our faculty YouTube channel. All right, as you can see on your screen, tonight we have someone from our Department of Physics this time, and his name's Dr. Kero Lau, and he will be talking to us more about what should we know about quantum technologies. About 2 decades ago, scientists realized that using the quantum properties of fundamental particles has the potential to dramatically improve the performance of our technology. Since then, significant progress has been made towards using quantum systems, and we're now very close to realizing practical quantum devices. In this talk, Dr. Kero Lau will give us a scientific overview of the principle behind quantum technologies and how they could impact our day-to-day life. I can't wait to hear Dr. Lau's presentation. Please help me welcome Dr. Kero Lau from our Department of Physics at Simon Fraser University. Over to you, Kero.
Thank you very much. Thank you for the introduction, Cynthia, and thank you for inviting me, and thank you for joining our event. So I'm Kero. I'm from the Simon Fraser University Department of Physics and also the Quantum Algorithm Institute in BC. So today I will try to spend the next couple of minutes to tell you what should we care about quantum technologies. So as the talk suggests, that the whole talk is about quantum. So I suppose you may have heard lots of things about quantum recently, ranging from some thing called quantum satellite that many countries is just start sending towards the space, and also once in every few months, and then one of the companies, say Google or IBM, they will claim that they have built a very powerful quantum computer that beats every computer we are using today. Also, you have seen lots of products try to brand their names with quantum, like the detergent or battery. And you will see it much more often in movies and games. So when the director doesn't know how to explain things, they just press the quantum button and everything seems to make sense. But no, of course, on the left-hand side, those kind of quantum branding and quantum science fiction are not the real quantum effects. But on the other hand, those quantum satellites and quantum computers, it's really some things that we are working very hard, and there are some really big scientific achievement. So therefore, my job as a physics professor is just to tell you, okay, what are the real quantum effects and what are not. But because you talk about that, we have to know what are quantums actually. So to know what is quantum, so we have to start contraring to the things that we have seen every day. And for example, sushi, chicken, restaurants, everything we are seeing today is that they call classical. So we know these kind of classical systems in centuries ago, and then we know how they behave, and we know what are the laws that they are obeying. So then in the early 20th century, so people thought that we have known everything about this classical system, so they try to improve the accuracy of the devices, and then they discovered that actually our every matter we are seeing today is just composed by some fundamental particles, such as atoms, electrons, or some even more fundamental elementary particles. So the most surprising thing they found was this kind of very, very small particles, and they behave very, very different from the particles, from the objects we are seeing every day. So what are the differences? So usually when I teach a class in quantum mechanics, the first lecture I will ask my students, so, okay, what do you know about quantum? So what are the differences about between quantum and classical objects? And usually they give me some very good answers. So first of all, they say, okay, yeah, quantum, as the name suggests, is quantized, so it should be involve something like discrete systems. And it's a low energy, and someone has heard about that. Yeah, there's something called quantum uncertainty principle to the quantum. So all of them are very, very good answers, but I want to highlight one property that separates quantum with classical objects, which is the superposition principle. So what is superposition? So we go back to 100 years, and then we go to look at one of the very famous milestone experiment in quantum physics, which is the Stern-Galerki experiment. So in that experiment, what do these two gentlemen do? Is they prepare a magnet, and then they mix the shape of the magnets a bit carefully, so that's they generate something called the inhomogeneous magnetic field, which means that the magnetic field strength is a bit different when we go from the bottom to the top. And in this particular case, the south pole is a little bit stronger. So therefore, if you send in a tiny magnet through the magnetic field, and then they experience a little bit stronger of the south pole magnetic field. So what these gentlemen do is to try to send in some atoms through this inhomogeneous magnetic field. And then you may have heard that atom has actually some electrons orbiting around, and those electrons actually have an intrinsic magnetic moment. You can really treat each of these atoms as a tiny magnet, and then we can polarize the magnets. We can net the atoms pointing to arbitrary direction before. So there's the magnetic moment of that atom can point to arbitrary direction. So if they point the atom towards the up in this case, and then they send through the inhomogeneous magnetic field, because the south pole is a little stronger, so the atom will just get attracted by the magnetic field and go upward. So if on the other hand, they send the atoms to pointing downwards, and then in that case, the south pole is on top, so therefore it will experience a repulsion force from the south pole magnets, and then the atoms will go down. So this is how the rule of the setup. If the atom, the magnetic moment is pointing upward, it will go up. If the magnetic moment point down, it will go down. So then here's a question for you. So then if we set this rule, and then we can send arbitrary atom inside, we can send atom pointing towards other direction. So what happens if we have the atom that the magnetic moment is pointing towards right? So I have 5 answers for you. What happens if we send into such an atom to the magnetic field? So answer A, we could go up. Answer B, we could go down. Answer C, it will go somewhere in between up and down. Answer D, it doesn't actually go through, but it will bounce back. For answer E, I'm not so sure, maybe half chance of half chance. So what do you think? Let's have a quick poll for a minute, and then let me know what you think. Yep, do you guess? Does it go up? Does it go down? Somewhere in between? Bounce back, or yeah, you are not quite sure. You just guess may go up or down with 50% chance. Okay, 10 seconds. So, all right, if when the poll is up, you can just let me know, and then we can take a look at the poll result. Oops. Okay, so I can see it's most of you say E, some of you say C, some of you say D. I think that's very interesting, and I can share what some actually those scientists, before they do the experiment, what they expect. Oops. But first of all, I have to close this window. So let me see how to close this window. Okay, here you go. So what these scientists, before they do the experiment, they say, yeah, if it is not pointing up or down, it is pointing towards right. So it should go somewhere in between, because of classical mechanics tell us that if you have something pointing towards other direction, and then whether it will experience a magnetic force that go up or down, depending on how much is tilted towards up and how much is tilted towards down. And in this case, if you're pointing have a atom pointing towards right, it seems that it is at the neutral point, it doesn't go up or down. So that's classically we would expect that the atom will actually first go through without deflecting, with something between up and down. But interestingly, this is not what they observe. They are actually observing something like they are really not sure what's the atom will go. So they prepare the experiment very, very well. Every time they make sure that they set the experiment sets identity. But it turns out no matter how accurate they prepare the result, they still get a probabilistic outcome. Sometimes they will get the atom going up, and sometimes they will get the atom going down. So it is a pretty remarkable result, and then I can summarize it at least there. Really interesting new knowledge that we gain with this experiment. So first knowledge is that now we know that quantum properties is quantized. So in this case, it will be the magnetic moment. So it is no longer a continuous number, depends on how much is tilted towards up, but rather magnetic moment can only be either up or either down. So it gives the name why we call it quantum, because some properties is now quantized, either up or down. And then secondly, but we say, yeah, but we can always prepare atom pointing towards arbitrary direction. So then how can we describe this situation? And quantum mechanics tell us that actually, if you have the atom pointing towards other direction, we have to express it in terms of what we call the superposition. So superposition, I represent it in the cloud, which is a mysterious stage that you may have in some science fiction that the atom will be both up and down at the same time. This is superposition. So usually a superposition is not just both up and down, but we have additional numbers, just as what I write in the crowd. That's tells you that if you really do a measurement to try to measure whether the atom is going up or down, it tells you what is the probability of getting the result to be up and down. So one of the examples is that if you are going to spin right, it turns out the superposition will be 50%, 50%, so half chance of up, half chance of down. But if you are pointing towards other directions, and then you will have a different combinations of up and down. So and in this combinations, you can actually use this kind of probability, or more formally we call it the amplitude of the state of the atom to be up or down, to actually store our information. For example, if it's up, we call it 0. If it's down, we call it 1. And if the superposition is somewhere in between. So that will be the quantum information we'll cover in a moment. And finally, the interesting result we see is before we do the measurement, before we send the atom through the magnets, and then the atom itself is in the superposition stage, both up and down according to some amplitudes. But after we do the experiment and after we measure whether it's going up or down, and then the atoms will either stay purely in up or purely in down. Which means that, okay, if we do one round of experiments, we find that the atom is pointing up, and then no matter how many rounds we pass the atom back to the magnet, it always goes up. So it is a interesting effect because initially it contains some information of either up or down, but after one round measurement, it only goes up either up or down, and then all the initial information about the superposition will be lost during this kind of measurement. So this is a striking effect because we are getting familiar with the classic object that, for example, we look at a bottle of water, and then if a bottle of water is full, and then no matter how many times we wash that, it's still full. Or if it's half full, no matter how many times we wash it, it's still half full. There's seldom a case that initially it's half full, but after we wash it, then it becomes, I don't know, something that jump up and down. Because our measurement classically doesn't destroy the state of an object. But this is a stark contrast in quantum mechanics that a measurement can actually destroy the information of a quantum object. And that's used a very important theorem in quantum mechanics, so quantum no-cloning theorem. It says that initially you have a quantum object that encode some information inside. So if you try to observe that and clone that information, and it is not possible, because whenever you try to observe the quantum information, you must destroy the information right away. So that's a very important theorem that has lots of application we'll talk about today. So before we go on, so now I can say that this kind of superposition principle can be generalized to multiple atoms. So for example, if you have two atoms, now I have the orange one and the blue one. And then generally to describe the state or the situation of these two particles or these two atoms, we have to describe it into all possible combinations of up and down. So in this case, because we have two particles, we have four different combinations. It could be both up, both down, one up, one down, and the other up, the other down. So then in general, we have to use a superposition of all four of these situations to describe the most general states of these two quantum particles. And this kind of effect is generally called entanglement, because in these situations, it's no longer possible to describe the one of the atom individually. So it's no longer telling that whether each of the atom is up or down or is pointing towards the other direction. Generally, we have to describe the two atoms together by this superposition of 4 different situations, and that is what we call the entanglement. It is the superposition of multi-particle state. So one of the interesting facts is this is the situation of 2 atoms, but when we generalize to n atoms, and then generally we need exponentially many different combinations to describe the situation. So in the n atom case, in general, we can have all the atoms pointing upward, one of the atoms pointing downwards, 2 of the atoms pointing downwards, so on and so forth. So in general, if you have more and more atoms or more and more quantum objects, you need an exponentially large memory or exponentially large possibility of states in order to describe what it will be the general situation of these n atoms. Okay, this is a short summary in the first part of my talk. So we go back 100 years and then to look at what is the Stein-Gallagher experiment. And then we found that by this simple experiment, we have 3 surprising knowledge gained. First, some of the physical quantities are quantized. That's given the name as quantum. And secondly, generally, we have to describe quantum properties by their superposition. And if you have more than 1 particles, and then we will have an effect of quantum entanglement. And finally, if you try to do a measurement, and then the measurement will generally destroy the superposition. So this is a very strange effect. So people are struggling to understand what would happen. So therefore, one of the founding fathers of quantum mechanics, Schrödinger, try to illustrate a very crude thought experiment. He said that, okay, yeah, maybe a superposition is difficult to understand, but perhaps we can look at a more lively example. So imagine that we put a cat inside a box, and then there's a box that contains a poisonous gas inside. And then now the gas is actually triggered by a radioactive source at random. So if the radioactive source doesn't emit a radiation, and then the gas is still contained in a jar, and then the cat will be alive. But on the other hand, if the radioactive source is emitting a radiation, and it will trigger the jar to be broken, and then to release the poisonous gas, and then the cat will die. So Hearn just say that, okay, if you do not open the box, and then what will be the situation of the cat? And he says that, okay, at that time, the cat will be both live and dead. It will be in the superposition of life and death. So yeah, I have to remind us no cat is harmed during I prepare this talk, so don't worry about that. And but whenever you open the box, then you can either get the cat to be either dead or alive. So this is like when we do a measurement, we destroy the superposition to be either up, down, or either the cat is dead or alive. So this doesn't seem to be a very good good explanation, because it gives us the impression that maybe superposition is just ignorant. So if we don't open the box, we don't know something. If we open the box, we know something. So does it mean that superposition is purely just because we don't really know what's going on inside the box? So I use a more modern example that this is McDonald's coupons. I think some of you may have received very often in your mailbox. So that each of the coupons will have a different food on sale. So imagine you receive this kind of a big paper of coupons, and you make them into pieces, and then you just put it into a wallet and randomize it. And then when you go to a McDonald's, you randomly pull out one of the coupons with the looking dots and give it to the McDonald's officer. And then in this situation, according to Schrödinger, does it mean that I'm actually ordering a superposition of food, say a superposition of coffee and burger? The answer is no, this is not a superposition. This is just ignorant. So how can we understand this? So when we go back to the Stein-Gallagher experiment, so when we send a atoms pointing to us right to the to the mass, and we get a random outcome. So quantum mechanics tell us that when we have the superposition of the atoms, it is actually a complete description of the state. So which means that we cannot get more description about the state. This is already everything we should know about the state. So it's a complete information, it's a full information. So the probability is just introduced when we try to measure the atoms, and then it will just collapse to either up or down. So the measurement destroys the superposition and generate the probability. But initially, before we do the measurement, before it's any passing through the mass, we actually have a full information about the atoms. So this is in stark contrast to how we interpret the results when we send in an atoms that we don't know whether it is going up or down. So in that case, if this is the case of the ignorance, so initially we don't know whether it is going up or going down. And then the measurement just reveals the unknown information that we know, whether it's up or down. So the interpretation is completely different, but can we really distinguish between both of this case, both the superposition or the ignorance? Actually, it is not that difficult. If you just, what you need to do is just rotate the magnetic field by 90 degree. So that in this case, if you send in a atom that's pointing right, it's always going towards the right with 100% certainty. But on the other hand, if you are sending randomly up or randomly down through the mass, and then you will see that it will go down with 50% go to the right and 50% to the left. So this gives us the intuition that, okay, to distinguish between the superposition and ignorance, the thing you should do is to change the way you measure, and there should be one configuration of the measurement setup that can tell you the difference between whether it is the superposition or the ignorance case. So, is there any do you convince by this observations? And I think that at this point, when I give the talk, and most of my students is just looking even more confused by the fact that, okay, there's superposition, ignorance, and the measurements. What are you talking about? It is completely natural because this is not what we have seen every day. And that many people are confused by this concept when they first seen it, including one of the most famous and important physicists in the world, which is Albert Einstein. So in 1935, Albert Einstein tried to formulate his ideas of why he don't like the idea of quantum mechanics, those superpositions, kind of stuff. And this is a concrete statement in his most famous paper in 1935. He believed that, so when we are physicists, we are looking for a physical theory to describe the universe. That theory should be able to predict with certainty what the system behaves. So if you have the theory that tells you, oh yeah, if you go to do the experiment, you will just get some probability of getting either of the outcome. It just means that the theory is bad. So there's something missing in the theory that we don't know about that. So Einstein tried to substantiate his claim with an experiment. So this is a modification of his thought experiment. It says that, okay, yeah, your quantum mechanics guys say that there could be superposition. Let's consider a superposition state that both particles can be both up or both particles can be both down. And then after you prepare this kind of superposition stage, you separate the two particles, one sends towards one direction, the other sends towards two direction. And then those can be sent very, very far apart, say one on the Earth, the other sent to other galaxy, light years apart. So quantum mechanics tell us that before we do the measurements, when the atom is traveling in a free space, and there's nothing disturbing the system. So that's the quantum state of this system remain unchanged. But however, if you do a measurement on one side, all of a sudden the other side would becomes a definite state. So for example, in this case, if we measure the orange atom on Earth to be on the up, all of a sudden the atom from the far galaxy, in the far galaxy will also becomes up. And Einstein thinks that this is not possible because there is no influence can travel faster than light. And then, but quantum mechanics tell us that all of a sudden when we do a measurement that collapses to either up and down. So therefore, the conclusion of Einstein is that, so it just means that quantum mechanics is a bad theory. Actually, quantum mechanics behave like the random McDonald coupons. That whenever you randomize it, whenever you draw the coupons from your waters, the food that is on the coupon is already determined. The problems of that random outcome is just you don't really know which coupon you're drawing, and then it's just you're just being ignorant. But on the other hand, the other founding fathers of quantum mechanics disagree with Einstein. The other quantum physicists believe that, yeah, the superposition is the correct way to describe what the quantum world is doing. So therefore, in the next 30 years, in 1935, there have been some debates on whether quantum mechanics is a complete theory, whether it's a good thing, a good theory that's completely describe what is happening in the world, or quantum mechanics is actually just an ignorant theory that there is some deeper version of quantum theory we haven't discovered that Einstein would call it a hidden variable theory. So there may be some extra theory that can take care of this kind of distribution of measurement outcome. It's just the current understanding of the quantum theory is not sufficient. So therefore, the current understanding of the theory is incomplete. So everything is more like a philosophical argument until in 1965, and John Bell come up with a brilliant, but it's a very straightforward idea. Yeah, if there's an argument and we are physicists, so the natural thing to do is let's do an experiment to test who is correct. So this is more or less what John Bell suggests. So imagine that you also have an entangled state, and then you are sending the two atoms towards two persons, so usually called Alex and Bob, A and B. And then what the Alex and Bob could do is each of them can pick a different measurement setup to measure the atom. And then in each of the measurement setup, it could be either the magnet pointing up or pointing left and right, or the magnet could be pointing 45 degree or 135 degree. But because the quantum is quantized, so in each of the measurements setup, they can only get +1 or -1 outcome. So what John Bell tells us is that, okay, you repeat this experiment for many, many times, and in each time, Alex and Bob are picking a different setup of measurement configuration. And then after you connect all the measurement outcome, you compute this quantity we call the S. So what is that? It consists of 4 terms that basically each of the terms it just tells us that if in the case that Alex is picking a particular measurement setup and Bob is picking another measurement setup, say in this case A1 and B1, they will get a measurement outcome with certain probability. So you get either +1 and -1, and then they just multiply it, and it will get also +1 and -1 with certain outcome. And then repeat the experiment many, many times to see what is the mean value of that outcome, the product of outcome they would get. So I will ask you to go through the details after you finish this talk. But what I would like you to emphasize is it turns out this S is a very important quantity that if Einstein is correct that there is some unknown theory behind quantum theory that haven't been discovered. And then the quantum theory is more like an ignorant theory that's like random McDonald coupons. It says that when you do the experiment and try to calculate this S, and that S has to be smaller than 2. But on the other hand, if quantum mechanics is correct that it is really in a superposition state, you can also always find a situation that the S is larger than 2. So what is the result? The results will be this year's Nobel Prize. So this year's Nobel Prize is awarded to Alan Aspers, John Clauser, and Seilinger for their contribution to actually doing this experiment by using not atoms but photons, but they are still entangled, and they found a violation of the Bell's inequality. So this is one of the more recent paper by Anton Seilinger, and they say that actually they do the experiment, they measure the S, and the S is equal to 2.73 plus or minus 0.02, which is something like 30 standard deviation, which means that it is a pretty reliable theory. And then we are now very convinced that S is larger than 2. And what does it mean? It means the Einstein is wrong and the superposition picture is correct. So this is a very important result. We saw that actually the quantum probability distribution is actually not a result of ignorance, but the nature really behaves probabilistically and with the superposition embedded. So I think some of you, I hope some of you understand more about that, but it's very natural that it's very hard to understand. And then even physicists are still debating how do we interpret this kind of a probabilistic result. But on the other hand, there are other branches of physicists say that, okay, if this is a strange result, yes, it is strange, but probably we can accept this is how the universe runs, and then try to come up with some ways to just utilize this kind of strange effect and put it into good use. And in the next couple of minutes, I will share what we call the quantum teleology, is the whole community or whole area of researchers try to use this kind of strange quantum effects and then just put it in good use. So traditionally, there are three main pillars of quantum teleology. So we use the quantum systems to sensing, computation, and communication. So today I will focus on computation and communication due to the limits of time. But recently, the community is expanding, and there are many more newer applications like generating random numbers, using radar, using improve the resolution of telescope, and many more. So if you click in quantum teleology, and I'm sure there are lots of new applications that are fun. So first of all, let's talk about quantum computer. So and to understand the merits of a quantum computer, we first understand what is a computer. And a computer is a device that processes data. You send in some input data, and then it will calculate the results according to what is the rule that you want the computer to calculate. And then the computer is fast or slow. It depends on if you have the same amount of data put into a computer, whether you can use a few resources to generate the result. For example, if it is you can use a fewer time to generate a result, it means that you have an efficient computer. Or if you can use a fewer RAM or fewer runs of the gates to generate results, we also call it an efficient computer. So therefore, the aim of the quantum computer is that is it possible that we are building a computer with quantum systems, so that the quantum system will allow us to use a fewer resources to generate the results when compared to traditional computer. So this will be the aim of a quantum computer. If we can achieve that, then we will achieve something called quantum supremacy or quantum advantage, which means that a device that's utilizing a quantum computer effects will be more powerful than a classical computer. So how does it work? So this is one of the simple examples. So imagine you only have a 1-bit classical computer. So just a computer can only process 1 bit of information. So because there's a 1 bit, there could be 2 informations, either 0 and 1. And imagine that you need to know both the results of processing 0 or 1. So in general, you need to run the computer for 2 times. You have to put in 0 to the computer. You have to put in 1 to the computer to get both the result of 0 and 1. So what happens if you do have a quantum computer? In that case, the interesting thing, you can prepare the input to be a superposition of 0 and 1. The input quantum bits, or what we call the qubits, can be both in 0 and 1. So that if you put into a quantum computer by just one run of the quantum computer, you will get both the results of 0 and both the result of 1 in a superposition state. And the most interesting thing is this kind of effect can scale up. Imagine that you have an n-bit classical computer. In general, if you want to know all the information, of the input, you need to run the classical computer for 2 to the power n times. You have to send all the bits to be 0, all the bits to be 1, one of the bits to be 1, or others to be 0 into the classical computer in order to know what will be the outcome. But interestingly, for quantum computer, you can actually prepare all the inputs in the same time in a superposition stage. And by just one run of the quantum computer, all of a sudden, all the results will be obtained in the superposition stage. So it seems to be extremely amazing because you just need one run and then you can do something that a classical computer will need exponentially long time to calculate. But is it really true that quantum computer is so powerful? That is science fiction, because actually there's one constraint. So remember in the Schrodinger cat says that if we don't open up the box, that the cat will be in superposition. But if you open the boxes, it can either be dead or alive. So yeah, same thing in quantum computer does. Although the quantum computer can generate superposition or the exponential many kinds of outputs, but whenever we do a measurement, we just have one of the results randomly popping up. So then in that sense, it doesn't seem to be so advantageous, because yeah, you can generate some result, but if we cannot read it out, so what is the point of that? So it turns out that there are some clever trick to can decide some algorithms so that, yes, although the quantum computer can tell us one result, but if we can make the algorithm so that only the results we care that will be read out, and other results that we don't care will not be read out, then we can still win. So what do I mean by that? So here's one of the famous example of the growth search algorithm. So imagine that you are doing a searching. For example, you go to a library in the weekend and you want to look for a book. Of course, you are not looking for the physics book, you are looking for a comic. So classically, how can we look for the books is we go to the bookshelf and we just pull out the book one by one to look at the title to see whether this is a book you read. And then if it's not, you just put it back to the shelf until you find the correct book that you want. So on average, if you have n books, you need to do this kind of a process for n times. You have to keep putting a book, look at the title and put it back for n times. But what happens if you have a quantum U to look at the books? You can actually create a superposition U to look at all the books at the same time, and then put it back at the same time. So quantum growth algorithm tells us that if you have this kind of superposition stage, you just need to check the books for square root n times and find the correct books. So for example, if you have a million book, classically, you need to check the books for a million times in order to find the correct book. But quantum mechanically, you just need 1,000 times, which is a huge improvement. So why is quantum mechanics helpful here? So it's because the quantum mechanics only tells us the information we want, which is where the comic book is. It doesn't tell us the information that we don't want. But on the other hand, classically, it tells much more information that we may not need. For example, it tells the first book is E&M, the second book is optics, the third book is general relativity. But these are the information we don't care. We just want to know comic book is in the fourth book. So therefore, quantum mechanics, if we decide the algorithm correctly, we'll just read out the correct information that we need and ignore the information that we don't want. And in this way, we can achieve a quantum advantage. So searching is just one of the examples of how quantum computer could be advantageous over classical computer, and there can be other examples such as breaking all the classical security code you are using today. But the simulate chemicals reaction, one of the reasons is that the chemistry is actually the interaction of atoms, and atoms is actually quantum particles. So if you use a classical computer to simulate chemical reaction, you actually need a very, very big classical computer to take care of all the possibility of the electrons and atoms is orienting. But if you are a quantum computer, it's automatically take care of those kind of superpositions, so it has a huge advantage. And more recently, people think attempting to apply quantum computer to machine learning, and then people found that yeah, if you have a quantum AI, is even more efficient than classical AI. Of course, this is not exclusive needs, and then in fact, someone has made a website to include all the known quantum algorithms that we know. So if you're interested, you can take a look on that. And I expect that there will be more and more algorithms that are coming up in the future, and more for you to discover. If you come to the SFU, go to the Quantum Algorithm Institute, and it's probably something fun to study. So the next application I want to say is communication. So as it suggests, communication is just sending information from one to the other. So usually there are different types of advantage by using quantum. One of the advantages that maybe you are using quantum, you can send more information by sending a single amount of physical carrier. But that is only advantageous under a very restricted situation. So I want to focus on the second part, which is about the security of the message I'm sending. So imagine that this is how we do classical communication today. By picking up a phone, we encrypt the information, send to the other person and the other person with the key, so decrypt the information when it knows what we are talking about. But in general, if there's some eavesdropper trying to steal our information, they can copy every information that's being transmitted through the channel. And as I told you before, that's one of the applications of a quantum computer is decrypt classical code. So therefore, if the eavesdropper is so powerful, they have a quantum computer, they can actually decrypt all the message that we are sending through the secure channels that we are using today. So this just means that if you have a quantum computer, every communication we are using today is not secure anymore. So therefore, people are thinking maybe we can use a quantum computer, a quantum system to transmit our information so that we can make it more secure. So the situation is like that if there's no eavesdropper, they will just encode the information in the quantum particles, such as a quantum photon, and then send to other person. So if the eavesdropping, the transmission is faithful, so everything sent by the person on the right hand side will be received from the person on the left hand side. But however, in the situation there are some eavesdropper, due to the northern no cloning theorem, whenever the eavesdropper try to steal some information through the channel, it must destroy the information. It might contaminate the information that's being transmitted. So therefore, this by checking whether the information is correct or not, so that the two persons that are transmitting information can actually verify that as an eavesdropper in between or not. So more specifically, you can imagine that when people are doing information transmission. So people are not directly transmitting information, but actually just transmitting keys to encrypt our information. So imagine that one of the person is trying to transmit the information, and then he transmits 5 keys of his 5 locks to the person on the left-hand side. And then the person on the left-hand side will receive 5 keys, but then by checking whether the keys are correct or not, they will also know that the eavesdropper is how many keys is trying to stolen by the eavesdropper. So in this case, for example, after they checking whether the results are matching or not, they know the 4 of the keys out of the 5 will be stolen by the eavesdropper. So then here is a question. So if we know that we have 5 keys transmitted and 4 out of the 5 keys has been stolen by the eavesdropper, so then how can we lock the information so that it remains secure against the eavesdropper? I give you 10 seconds to think about that, and then I will tell the answer. So if there are 5 locks, but 4 of the locks is already can be cracked by the eavesdropper, so how can we block our information and transmit it securely to the our receiver? So then the answer is actually not that difficult. So if we know that the eavesdropper only stole 4 of the 5 keys, then the thing we need to do is just lock the information of all the 5 locks. We don't know which one is stolen by the eavesdropper, but we know that at least one of them is not gained by the eavesdropper. So that's our information remains secure. So this is what we call this is the principle of what we call the quantum key distribution. Is by using the no cloning theorem, we can actually estimate how much information is obtained by the eavesdropper in order to estimate that, okay, how many keys and locks that we need to use to encode the information, so that even though the eavesdropper is stolen parts of the information, the remaining information will allow us to encrypt the information securely, so our transmission remains secure. Okay, so before I end the talk, I want to do the advertisement of what we will be doing in SFU. So my group is actually a quantum optics and quantum information theory group. So we are theorists, so we don't build a lab to make quantum device, but I have some colleagues building a lab to make the quantum device. So for us, we are theorists, so we mainly do calculations. So I do 2 kind of studies. So on the one side, I study information processing, all the applications I have talked today, communication, computing, and also sensing. So I looked at applications and see what do we need to implement this kind of applications. And after we know what they need, we go to the physics system. So we also study physics, and we study different kind of quantum systems like trap ions, photons, spinons, oscillators, and blah, blah, blah. And then we see, okay, if this is something you need, and then I try to look for the correct platform to implement this kind of technology. And on the other hand, by studying this kind of physical system, we will also know what are the advantages and disadvantages of this kind of system. And then more importantly, if we know the disadvantage or know the errors of this or imperfections of this system, we will go back to see, okay, if we have some imperfect devices, how well we can implement this kind of technology. So the ultimate goals of the research in my group is, can we use imperfect devices, which we know that in practice, all the device has to be imperfect because our technology is not advanced enough to make a perfect, purely working device. So that's, can we still enjoy some of the advantages of quantum technologies by using an imperfect device in the practical situation? That would be the interesting thing that we are looking at in my research group. So as a summary of my talk, so I first review what is the Stern-Gala experiment. There are 3 interesting quantum effects we've learned from there. First, some of the quantum property is quantized. That is the name of quantum. So it is not a continuous system, it is a discrete system. So that's why it's called quantum. And then a second difference, we know that quantum state generally involves superposition. In order to describe the situation of a quantum object, we need a superposition. And when we generalize to multiple objects, then it has the entanglement, and that entanglement actually gives rise to the quantum advantage of a quantum computer. And finally, when we do the measurements, it actually destroys superposition. That gives rise to the no cooling theorem that's guaranteed the security of the computation. So that's all for my talk. So if you are interested, feel free to send me an email, and I'm happy to answer questions, or you can go to my group research group website to see what will be our updated research result. Thank you for your attention. Have a nice evening.
All right. Thank you so much, Kero. At this point, I'd like to invite the people in the attendee room to start typing their questions or comments. We have a few that have come in, but let's give it a minute or so for people to think through their questions, and even if they're comments, we'd welcome those as well. I do appreciate your slides, Kero. I just wanted to say how amused I was with all the animations, the cat, the little figures. Really, it really helped us understand your presentation. Yep. So thank you so much for doing that. And plus the whole question that helped engage with your audience and get to feel what they were thinking as well. And even if they were not sure, that's fine too, because that's precisely why we're doing these presentations.
Yeah.
Anyway,
there's no question as stupid question, so every question is welcome. So
thank you. There have been a few. I'll address a few questions on the Q&A box first of all, we are not sharing the slides from tonight's presentation, but we are sharing the recording. So the recording will have a screen shared slide presentation as well. So please refer to that, and it will be coming up on our faculty website as well as our faculty YouTube channel. First question is, can you describe how qubits are physically stored and processed?
That's a good question. So as in the first slide, I actually told that there are lots of different kinds of physical systems. So then in each of the system, and actually a different degree of freedom can be encoded in qubit. So one of the example is if you have a photon, and then you know that I don't know if you know that the photon can actually oscillate, or the electric field of the light can actually oscillate in 2 orthogonal directions. It can oscillate in a vertical, and it can oscillate in a horizontal. So then in that case, what we mean by processing the qubit is just rotating the vertical polarized lights to become horizontal and vice versa, or generally rotating the direction of those kind of polarized lights. So that's what we can do is by using some polarizer. So we have some polarizer that the light, if you are sending in some vertical polarized light, put the polarizer, it will just tilt a little bit. So this is one way how we can process the quantum information encoded in light, and it's also one of the common things that people are doing in quantum communication, because people send information through as photons through a long distance. And then, but this is not the only way we encode the quantum information in physical system. So another very common physical platform is atoms. So you can imagine the atoms could be in the ground state, which means the electron is the lowest energy. But you can also excite the atoms to be in some excited state, but it's stable, metastable, so you can store the atomic excitation for some time. So in that case, the processing the quantum information would be like promoting the state from the ground state to the excited state. And it can be done by sending some laser field with a particular strength and time. You can actually create whatever superposition stage between the atomic ground state and atomic excited state. And there are lots of different examples depending on what kind of platform you are doing. And this is what the whole community is working on. So we have been trying different kind of platform and different kind of platform. One of them, some of them may have the advantages. You can store the quantum information for a longer time. And as a matter of fact, actually, one of my colleagues is holding the world record of storing quantum information for the longest time in the world. And this experiment is actually done in SFU, so it is pretty impressive. But we generally, with physicists, are trying different kind of platforms and see how we can use them. Some of them may have a longer storage time, some of them may be easier to manipulate. There's no clear cut to which one is the best.
Right.
So thanks for your question. Yeah.
Thank you. I'll read out the next question. Is it possible that quantum entanglement exists in nature? And if so, what are the consequences of large-scale quantum entanglement?
Okay, so that's a good question. Actually, entanglement exists everywhere. So even if you pick up a piece of metal, and then there are many electrons inside a piece of metal, and that those electrons are interacting. All of them are interacting, and generally they are in an entangled state. So, and then the point is that that actually to your point is so entanglement have different types. So sometimes entanglement is useful, but sometimes entanglement is not quite helpful. So then the key point of quantum computer or the quantum technology is to create the correct type of entanglement that we want that has an advantage, and avoid those kind of bad entanglement that is doing nothing good. So therefore, although entanglement is everywhere, but it's not the case that more entanglement is better, but you just need the right type and right amount of entanglements. And furthermore, so if you have many electrons, of course, they're in a entangled state, but can you really get this entanglement state from the electrons? This is the problem. So therefore, in addition to creating the right type of entanglement, you also need the way to control each of the particles that contain the entanglement. So that's why there are lots of different physical platforms, engineer quantum platform, that we can actually engineer some system to create the right type of entanglement. And at the same time, we can control each of the degree of freedom, so that we can use each of the object as our quantum computer to do calculation. So by just having the entanglement, it might not be so helpful. Yeah.
Right.
Good question. Yep.
Thank you. Next question is on applications. Can you give some examples of how to use a quantum computer? What kind of data can we work with? And I think the question was more zeroing in on breaking classical security codes. How can we use a quantum computer for this?
Okay, so yeah, as in that page, I actually introduced lots of application in quantum computer. So that breaking cryptographic code is just one of the applications. I think it is one of the application that got lots of attention at the very early stage of the development of quantum computer. But we now realize that we actually need a very high accurate, very highly accurate quantum computer to achieve that, which is a bit beyond reach at this moment. So don't worry. So you won't wake up tomorrow and all your Instagram photos have been stolen by a hacker. So, but what we think is a more recent application or more imminent application would be something like a simulation process and also machine learning. So we found that for this kind of application, actually the accuracy, we might not need a very accurate quantum computer and still get some useful stuff. And in particular, chemical simulation, as I mentioned, chemistry is an interaction of atoms and molecules. And those kind of stuff are quantum objects. And using classical computer to simulate these kind of objects is very, very resources demanding. So quantum computer can hopefully actually boost the efficiency of chemical simulation. And by boosting chemical simulation, for example, we can make drugs. We can identify the drugs easier, or we can study we can identify some process to make some chemicals faster, which is has a huge application in industry and also biology.
Mm-hmm. Well, speaking of breaking security codes, you spoke earlier about eavesdropping and hackers and keys being hacked. Can you estimate costs on how to encrypt securely? What are the costs involved in this?
Yeah, so I mean that's if you need to use quantum cryptography, of course you need to change some of the hardware. So it is not like you download a new version of the software, you can do that. So you need to install some quantum detector and also quantum light source. But so far I understand, so I'm not an expert on that, but so far I understand that actually in some parts you can reuse the infrastructure you are using today. And people are trying hard to send the quantum light through the commercial fiber that's already transmitting the internet signal that we are using today. So then, and there's already some demonstration that you can use this kind of fiber, existing fiber, to transmit quantum signal across hundreds of kilometers or tens of kilometers. Mm-hmm. So therefore, definitely you need to change something, and then it's not just a software update, but that something may not be too demanding. Maybe you just unplug the current router and to a quantum router, and then you can already do that.
Interesting.
Mm-hmm.
Next question. Why did it take so long for physicists to disprove Einstein's theory?
That's a good question. Yeah, so I think so there are two stages, I would say. So from 1935 to the Bell's theorem, I would think the discussion is mostly philosophical. So they didn't realize that actually you can actually do an experiment to distinguish between those two. And also, I think that is not the mainstream problem at that time. So I think at that time, the physicists would believe that, okay, yeah, you have some new theory, and it seems to describe very, very well. So even though we don't know so whether the theory is ignorant or it is complete, but the prediction of quantum mechanics is very, very accurate. And there are so many new discoveries at that time, so that people will think, oh yeah, this kind of philosophical argument, we can put it outside, but we just apply the newly discovered theory. Who cares about whether it is complete or not, but we can just use it to do something useful, to describe all the new phenomena discovered in early 1930s. So therefore, I would say the whole studies at that time is not mainstream. And in fact, when John Bell tried to come up with the Bell's theorem, he did it in his leisure time. So he is not working full time on the Bell's theorem. He just I remember something like on a holiday or so, and he said, "Oh yeah, maybe I could think about that a bit more," and then he finds something. So and then he also said that if it is not possible to find a full time job to think about this kind of stuff. So it's just by accident that they find it turns out they have some new discovery.
Right.
So that's the reason why, because it's not the mainstream. But then the problem is why do we need to take so long to go from Bell's theorem to the realize or to prove the experimental proof? It's because of the experimental apparatus at that time, the efficiency is very, very low. Mm-hmm. So one of the main requirements is that we need to create an entanglement source. But at that time, all the entangled photon sources, either the quality is so low that we cannot use the entanglement for our purpose, or you need to wait a very, very long time in order to get one of the click. But in order to prove the result, you need many, many clicks. So therefore, one of the achievement of this kind of Nobel laureates this year is that they actually come up with a photon source and measurement device which is efficient enough that you can collect sufficient data to disprove to show the violation of health inequality within some reasonable time and reasonable accuracy. So this is a major scientific achievement.
Right. Next question. Why can't we see quantum effects in daily life?
Yeah, I think this maybe is the other question that can large objects be quantum entangled. So because entanglement and quantum effects is related. So this is a good question that actually for physicists, we believe that quantum objects, so quantum mechanics actually describe every object, no matter it is small and large. But we also know that we may have heard about the wave and particle duality of quantum objects. So that quantum objects behave both wave-like and particle-like. So if they behave like particles, it is more like the classical object we are seeing every day. But on the other hand, if they behave more wavy, and then you will have some quantum effects like superposition and so on and so forth. And then it turns out if the object is more and more massive, it's larger and larger, the wave-like feature is more and more difficult to observe. And it is difficult to observe, meaning that we need a measurement apparatus to be more and more accurate in order to distinguish the quantum effect for a larger object. So therefore, we are still working on keep improving the accuracy of our apparatus, and I can share what would be the most updated progress is. So in the very beginning, when we talk about quantum objects, we usually talk about atoms, very, very low energy light is like single atoms or just multiple atoms, maybe 20 or 30 years ago. So in very recently, we are able to observe quantum effect in what we call the macroscopic object that involve 10 to 12 atoms, which is a billion atoms. So it is like a billion-fold of improvement. But when you are talking about, can we observe a quantum effect on a cat? I think that we still have sometimes to develop the sufficiently accurate devices to measure whether the cat could be in the superposition of something. But we believe that we can go to there at some point.
So if large objects can be quantum entangled, can this be applied in very tiny objects as well?
Yeah, and actually we start the other way when we start with a tiny object and then we try to generalize it to a larger and larger object.
Okay.
Yeah.
I'll end with this last question. Can the effects you describe be found in other quantum systems?
Oh, of course. So as I mentioned, so there are lots of different types of quantum systems. So you have atoms, electrons, light, and we also have some elementary particles. So then there's a big area of research of what will be the best quantum system we are using to find to do the quantum topologies. In other words, so whenever you have a system that is quantum in nature, we can already see this kind of quantum effect. So right now there are a couple of forerunner of implementing quantum topology. So one is light. So because that's what the Nobel laureates are developing. The other is atom that's mentioning. And then the next will be what IBM and Google are building in their quantum computer, which is they use superconducting circuits, so that you can imagine the superconductor is like a device that's the resistivity is very low. So that's if you have a current, it doesn't decays. And then it turns out the reason why the superconductor will retain the current for a long time is because of the quantum effect. So it is actually a quantum object. So and then the next will be electrons, and then electrons can be both free electrons that move around, or some people can have some crystals, and then the crystal can take out one of the atoms, and then that will create a hole inside the crystal, and that hole can trap an electron inside, and that's what we call the defect center. So there's lots of quantum systems like that. So there's both quantum first of all, and second, we can retain the quantum effects for a long time. And finally, we can actually control the quantum system so that we can mix them to behave in a way that behave quantumly and can observe the quantum effect. So there are lots of systems actually. So it's not just atoms and electrons and photons.
All right. Well, thank you so much. I think I've
There's
gone through
one
the
more question.
questions. There's one. Oh, there's one last one. How can you define up or down?
Yeah, up and
For
down
up
just
to be
mean
down, all you have to do is tilt your head, she says.
yeah, yeah. Very good question. Yes. So usually before we do the experiment, we have to align our apparatus in some direction. So the most likely we have to point our magnetic field towards a particular direction, and then for simplicity, we just say if the atom is pointing towards that direction, it is up, and then atom is pointing in opposite that direction is down. And by pointing, I mean the magnetic moment, so that the atom actually have a tiny bit of spin, and that spin can actually point to opposite direction. So of course, yeah, if you tilt the head, and it can go from up and down, but tilting a head is like you are changing the measurement apparatus, so you are looking at the system in a different way, and so it's just like in the apparatus I'm describing. So you have the magnets. If you tilt the magnets, of course, the up and down are pointing towards different direction, but it's equivalent to measuring the quantum system in a different way.
Well, thank you so much, but I can't help but read out. I can't help but read out one more comment here, and I'm sure I was really amused with your presentation and all the graphics on your slides, and I can't help but read this last comment. No cats were harmed in the making of this presentation.
Oh yeah, no
that
cats
is
are
so
harmed.
cool.
Yes, yeah.
Well, thank you so much, Kero, for your presentation.
Thank you for inviting me. Yeah.
I hope you enjoyed that, and I'd like to thank everyone who engaged with us tonight, and thank you to all those who typed in their comments and questions. I hope to see you again for the next session. It's happening on April 25th. You will receive information on your email as well as the registration link, but that's the title, and our presenter will be from the Department of Statistics. So I hope you can join us then. I'd also wanted to thank our colleague from our MEX team who's been on the back end helping us with our IT needs. Thank you so much for always supporting this series. So thank you so much, Kero, for joining us tonight. Lovely to have you. And to everyone else, I'll see you in April, and enjoy the rest of your evening. Thank you.
Thank you. Bye-bye.
Bye now.